For countless generations, humanity has looked up at the night sky in awe, captivated by the vastness of space and the mysteries hidden beyond our world. In the 20th century, scientists introduced the Big Bang Theory to explain the origin, evolution, and ongoing expansion of the universe. While widely accepted, this theory still leaves many fundamental questions unanswered. In recent years, new discoveries have only deepened these cosmic puzzles. A particularly shocking moment came in 2023 when NASA's James Webb Space Telescope detected celestial objects that appear to be older than the universe itself, a finding that stunned the scientific community and sparked intense debate. Could stars really predate the very universe they inhabit? Webb's observations challenge our current understanding of space and time, hinting that our entire model of the cosmos might require a complete rethinking. These are the kinds of mind-bending questions we'll explore. If you're intrigued by the universe and eager to stay updated on the latest discoveries, don't forget to subscribe, hit the like button, and turn on notifications so you never miss a new insight. Roughly 200 light-years from Earth, in the constellation Ophiuchus, lies a star named HD 140283, an astronomical enigma, nicknamed Methuselah, after the biblical figure famed for his long life. This star isn't just remarkable for its blazing speed of 4,483 kilometers per second, but for its extraordinary history. About 1 billion years ago, during the Milky Way's early formation, our galaxy collided with a smaller one, and Methuselah was among the survivors. Yet what truly sets the star apart is its age. Early estimates suggested it was 16 billion years old. More refined calculations later adjusted that to about 14.46 billion years, with margin of error of plus or minus 800 million years, still older than the currently accepted age of the universe. 13.8 billion years, based on measurements of cosmic microwave background radiation. This apparent paradox, how can a star be older than the universe it exists in, has forced scientists to reconsider how we determine the ages of stars and the cosmos itself. It's a mystery that continues to challenge the foundations of modern astronomy. To understand this cosmic contradiction, it helps to know how astronomers estimate stellar ages. Stars like our Sun maintain a steady size and temperature over billions of years, making age determination incredibly tricky. Scientists must examine subtle changes in a star's light and color and match those observations to complex models of stellar evolution. One of the primary methods used is gyrochronology, which estimates a star's age based on its rotation. Like spinning tops that slow down over time, stars gradually lose angular momentum. By measuring a star's rotation rate and comparing it to others with known ages, scientists can calculate a rough age. Methuselah is undeniably ancient. But instead of asking whether it's really billions of years older than the universe, perhaps the better question is, could the universe itself be older than we think? Trying to wrap our heads around 13.8 billion years isn't easy. Imagine condensing the entire history of the universe into a single calendar year. The Big Bang would occur at midnight on January 1st. Earth wouldn't appear until late on December 31st, and all of human history would occupy just the final seconds before midnight. Astronomers derive a universe's age by analyzing light from extremely distant galaxies that formed shortly after the Big Bang and calculating redshift, the stretching of light as the universe expands. This data gives us the widely accepted estimate of 13.8 billion years. However, a bold new theory proposed by physicist Rajendra Gupta at the University of Ottawa challenges this figure. According to Gupta's research, the universe could actually be around 26.7 billion years old, nearly twice the current estimate. This dramatic revision could explain anomalies like Methuselah and reconcile long-standing inconsistencies in cosmological observations. Rajendra Gupta has revisited a 1929 theory originally proposed by Swiss astronomer Fritz Zwicky, combining it with modern discoveries to propose a bold new idea. Gupta suggests that protons may gradually lose energy over vast stretches of time and space, a concept that challenges a conventional explanation of redshift, which is typically attributed to the expansion of the universe. Instead, he posits that redshift might result from a combination of cosmic expansion and this energy loss. If correct, this hybrid model could fundamentally reshape our understanding of the universe's true age and help resolve long-standing cosmological debates, many of which have been intensified by recent NASA Space Telescope findings. Gupta's theory expands upon the old, tired light hypothesis and introduces a concept known as evolutionary interaction constants, first hinted at by theoretical physicist Paul Dirac. Dirac proposed that the fundamental forces of the universe may not have remained constant, but could have evolved over time. This idea opens the door to a radically different view of cosmic history. It's important to remember how much our perspective on the age of the universe has shifted over time. In the 1920s, Edwin Hubble estimated the universe to be just 2 billion years old. Since then, technological advances and refined observations have revised that figure to the currently accepted 13.8 billion years. Still, when we compare the timeline of human history to the universe's lifespan, it's barely a blink in cosmic time. Yet the questions we ask are as vast as space itself. Meanwhile, scientists are uncovering surprising insights about our own Milky Way galaxy. Recent observations have revealed that stars on its outer edges rotate much more slowly than those in other galaxies. One possibility is that the Milky Way contains significantly less dark matter than previously believed. Despite being invisible, dark matter exerts a strong gravitational influence on galactic structure and motion. Alternatively, our entire model of how dark matter is distributed across the cosmos might be flawed. These revelations come from data collected by the European Space Agency's Gaia mission, which has mapped the positions and motions of nearly 2 billion stars in our galaxy. The findings have led astronomers to reconsider how stellar behavior correlates with mass distribution, especially at the galactic fringes. Since the speed at which stars orbit depends on the galaxy's total mass, including visible matter like stars and gas, as well as dark matter, recalculations are shaking up previous estimates. A recent Gaia-based analysis suggests that the Milky Way's total mass might be around 200,000 billion times the mass of our Sun, roughly 5 times lower than older estimates. This could point to a surprising shortage of dark matter, although uncertainties in satellite data or the models used could also be responsible for the discrepancy. As our instruments improve and more accurate data becomes available, we'll be better equipped to test these theories. Future space missions and technological breakthroughs will likely help unravel these cosmic mysteries. The James Webb Space Telescope, with its unprecedented capabilities, is already pushing the boundaries of what we can observe and understand. Beyond determining the age of stars and galaxies, JWST is helping scientists probe the nature of dark matter, uncover the hidden dynamics of galaxies, and explore the mysterious forces that govern cosmic evolution. Though the universe's expansion remains one of the great unsolved puzzles, emerging evidence suggests we may need to rethink our long-held beliefs. A central question persists. Do the laws of physics operate the same way throughout the entire universe, across all scales and eras? Could there be hidden forces or unknown processes influencing how galaxies form, how stars evolve, or how matter behaves? As our observational tools become more powerful, we may uncover findings that completely upend existing scientific paradigms. Researchers are beginning to recognize that we've only scratched the surface of understanding phenomena like dark matter, dark energy, and the fundamental forces shaping the cosmos. Every new glimpse, whether from ancient stellar remnants or distant galaxies, offers hints about the universe's workings. But more often than not, these revelations lead to even more questions, propelling the frontiers of human knowledge further than ever before. And perhaps one day, we'll find that stars and galaxies are not just younger or older than we imagined, but part of a much deeper and more complex cosmic story than we ever thought possible. This is driven by a shared desire to most important, highlights every organization as discovering concrete one related concept, concept of potential deals with how matter changes across the universe. This discussion how scientists track of events evolved over time. Some regions in space present galaxies, while others are larger galaxies. Scientists from various one such band light from distant sources, a phenomenon known as gravitational. This allows scientists to categorize therefore another category is cosmic microwave. Faint afterlife how much travel by studying geometry, researchers gain insight into photographs however, this data doesn't lie with large the uneven gravitational early this mismatch according to James Webb Space Telescope, whether the Hubble Space Telescope might have the fundamental flaw in our understanding of gravity hiding between these observations. The right side is thanks to AWS powerful researchers can now study cosmos despite this problem, dark matter and dark remain shrouded in space, while black holes our attention now being dark matter might also as scientists continue to analyze the foundations of modern cosmology are undergoing serious the telescope ability to measure galaxies challenge comprised of the cosmos of early universe massive galaxies this is just one of two possibilities. Either galaxies now for our understanding one emerging idea involves adjusting the standard framework in cosmology. It includes cold dark energy, cosmological lambdas, representing dark energy. Some physicists now speculate that dark energy together time interact with dark matter in ways we don't yet understand. This evolving form of darkness, often called quintessence, to explain why cosmic expansion rates differ across time periods. Other researchers are investigating alternative theories of gravity, such as modified Newtonian dynamics or scalar tensor theory, which tweak Einstein's general relativity on cosmic scales. These models aim to address the gaps and tensions in current observations, offering new ways to explain the universe's most puzzling phenomena. Public interest under Saturn's breathtaking solid solar telescope. NASA's attention to balance of planets like the Hubble Space Telescope and the Mars showing strange still without Voyager pressed chaos could reign. Traveling nearly every miles a day, orbital Saturn's widespread unknown intrigues Neil deGrasse Tyson and compelling insight only moon in the solar system with a thick known for famously championing the reclassification of Pluto as a dwarf planet. Tyson doesn't see this as a demotion, but as an acknowledgement of our evolving understanding of celestial mechanics. He emphasizes that orbits like Pluto's, steep, elliptical, and chaotic, are reminders of how much we still have to learn about the universe. Tyson often highlights how public interest in topics like Pluto's orbit can serve as a powerful gateway to scientific curiosity. By engaging with the unusual and sometimes illogical nature of space, people are invited to appreciate the beauty and complexity of our cosmos. Pluto, in all its orbital oddity, exemplifies that. Despite the alarms raised by some researchers, the general consensus remains. While Pluto's orbit is indeed chaotic and unique, it is highly unlikely to collide with Neptune in the foreseeable future. Still, The very possibility, however slim, serves as a potent reminder of how fragile cosmic order can be. Continuous observation, advanced simulations, and refined models are essential to maintaining our understanding of the solar system's delicate balance. Pluto's curious path may not pose an immediate threat, but it continues to challenge our assumptions and deepen our appreciation of the vast and dynamic system we call home.